Okay, so we're almost done. So the thing that we have come down to, we have the integral of 1 over 2 pi times the integral from minus pi to pi sine of n plus 1 half z f of x plus z minus f of x over sine of z over 2 dz. Now this function we call g of z. Okay, and we're using the fact that this sequence of functions here, this is orthogonal. And actually, if we pick the right weight, if we pick the right dz, like if we do dz over pi, this is actually orthonormal. Okay, and so what it shows us then is by Bessel's inequality, if I look at the sum, so this integral squared from minus pi to pi is equal to pi. So what I'm saying is the integral k equals 1 to infinity 1 over the square root of pi times. So sorry. Let me be clear what I'm saying. So if I look at this integral, so if I look at this function and square it and integrate it from minus pi to pi, the result is pi. Okay, so what it tells me then is that the integral of 1 by Bessel's inequality, this integral minus pi to pi sine of n plus 1 half z times g of z dz is less than or equal to 1 half times the integral minus pi to pi g of z squared dz. And in particular, if this is finite, it means that these terms go to 0. Sorry, I've got a k here and an n here. Let me keep the n here and make this an n here. What this says is that as n goes to infinity, each of these terms has to go to 0. So as n goes to infinity, these terms go to 0. Why is that? Why did I put a dz there? What's going on with me today? So what happens as this is a finite sum. If this is finite, this sum is finite. And so by the test for divergence, each individual term goes to 0. The terms go to 0 as n goes to infinity. So by the test for divergence, the terms go to 0 if the sum is finite. So all I need to do now is show that this g of z is square integrable. And what I'm actually going to do is show that g of z is a bounded function. So how can I do that? Well, g of z, so the absolute value of g of z is equal to the absolute value of f of x plus z minus f of x divided by sine of z over 2. Now, by the mean value theorem, this is equal to f prime for some c sub z that's in between x and x plus z times z, and then divided by sine of z over 2. Again, this is the mean value theorem. So cz is some number in between x and x plus z. Okay, well this is equal to the absolute value of f prime of the cz, and then times z over sine of z over 2. Okay, so if I divide here by 2 and multiply by 2 out here, I'm going to write it like this. The reason that I want to do that is because we learned in calculus that this function is bounded. In fact, the only place where there could be a problem is going to be when z is equal to 0. But you learned in calculus, you learned in your Calc 1 class, that the limit as h goes to 0 of h over sine h is equal to 1. You probably actually learned sine h over h, but since the limit is equal to 1, you can flip it like this. The same argument shows this is equal to 1. Or using the, you can divide the limits. Okay, so this is bounded by 1. So the thing that I have there in a circle is bounded by 1. So this, sorry, I need to do absolute values there. So this is less than or equal to 2. Now, we're assuming that f prime is continuous. So if f prime is continuous, I'm looking for minus pi to pi. That's a closed interval. If, in particular, it's a bounded interval, so it means that f prime is going to be bounded both above and below. So f prime will be bounded both below and above on the interval minus pi to pi. So in other words, this is less than or equal to some constant we'll call m, and then this is less than 1. So overall, my function g of z is less than or equal to 2 times m. So in other words, if I do the integral from minus pi to pi of g squared, this is going to be less than or equal to the integral minus pi to pi 4m squared, which is equal to 8 pi m squared. In other words, this is finite. Okay, and so that finishes the proof of the convergence of Fourier series for a continuous function where f prime is also continuous. I don't want to. I'm not going to make a video showing the thing about converging to the if you have a jump discontinuity. I'm going to let you guys read about that, not because it's not important, but because I just want you guys to kind of maybe focus your energy on other things. I'd rather you understand this proof and spend your time understanding this proof, and then you can go back and understand the extension to the case where f is only piecewise continuous and the derivative is only piecewise continuous. But that's it. That's kind of the last new video that I'm going to make for this class. So thank you for taking this class. I will see you guys in the discussion forums.